Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WAEC, JCE, KCPE, IJMB, JUPEB, KCPE, BECE, SSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Hello, welcome to physics class. Today we are going to be looking at elasticity. In elasticity, we consider the properties of a material because there are several materials and nature has given us a whole lot of them and variety of materials. And most of these materials, some can react immediately to a force applied. Some can break when force is applied. Some can accelerate when force is applied. Some can remain stable when force is applied. But some of these materials, what they do when force is applied is extend or enlarge a little and come back to the original position. Looking at what you are seeing there on the screen, you see that this particular material standing between two supports, when force is applied, it extends a little and later come back to the normal position. And this is the reason why you can use your car, pass through a bridge, and then sit on a chair, and yet they don't break. For this reason, I want to welcome you to this topic called elasticity. Now, this is also one of the examples of the ability of a material to be able to extend and return to its original state. And this one you are watching on the screen is one of the examples, like cantilever. So, by the end of this lesson, you should be able to define elasticity and give examples. Then you state Hooke's law and define stiffness of a spring, and then apply Hooke's law to problem solving. If you are ready, let's get started. Now, when we talk about elasticity, we talk about a material, the ability of a material to be able to extend and later comes back to its original shape. The ability of a material to extend and then comes back to its original shape. For example, look at the spring here, all these springs. When force is applied between the ends, you realize that these springs can extend and also come back to its original shape. Now, we have to talk about Hooke's law, Robert Hooke, and then talk about what he stated concerning this elasticity and his findings on elasticity. And he came up with the definition, and he said that provided the elastic limit of an elastic material is not exceeded, that the force applied on an elastic material is directly proportional to the extension. So he says that if you don't go beyond the elastic limit of a material, that means you don't apply so much force that will distort the body, that the force you apply will be equal to the extension that you are going to experience. Now, looking at what you have on the screen, the picture, this is the original length of the spring. Now, when this string is applied with a force, let's assume that this is a body or a mass, and a mass can apply a force. And when this force is applied in this direction, you see what happened? The spring becomes a little longer. Now, this additional length on this spring is what we call extension. Then, when more forces or more bodies or more masses are applied on this spring, what you notice is that the spring also increases even more, and that is the extension And that is what Hooke's law was saying. And according to the law, or Hooke's law, we said that the force you apply on a body is directly proportional to the extension, whereby we have that force is equal to Ke, where K is given as the stiffness of a material. Or we can also say that the K is given as force constant. So there are a few other names that they call them, but then you also know that this is it. And the SI unit of K is given as Newton per meter, such that when you make this K the subject formula, you have F all over E, and then the SI unit is Newton per meter. Now, the reason why we have this is because remember that this minus, sometimes you have this minus, which is there, tells you about the opposite force. Remember what Newton's third law says, that force applied is equal and opposite. So there is an opposite force to the movement of the mass. So there is also a force pushing upward. That is the essence of the negative sign. Now, in terms of an explanation for what we call the graph of Hooke's law, that is exactly the force extension graph for a metal, because most of what we are going to be learning now is mostly all about the spring, and that is metals. So when you have this graph plotted such that when you have a force plotted on the horizontal axis, Newton, and then extension in meter, then you have a straight line graph. You now say that Hooke's law is obeyed. So in such experiment like this I'm showing you now, in such experiment, you imagine when we keep adding more masses to this spring. And remember that this spring, we talk about the force constant, or the stiffness of the material, or the constant of proportionality of the material. I mean, the extent to which a material can be extended. Now imagine more forces, you keep on adding more forces to this spring. What will you notice? You notice that a time will come when the spring will no longer be able to accommodate the more forces, or the spring will not be able to carry the forces that are being applied. At that point, then we now say that Hooke's law is no longer obeyed, because at that point, the force is no longer going to be proportional to the extension. Then the material distorts or sags, so that when you remove the force, it cannot come back to this original length. Then we say that then there is a deformation, or Hooke's law is not obeyed. Now, the graph you are seeing here on the screen is the force extension graph for a metal. Now, what happened is this. There are different stages of this graph. Remember, if there is a straight line from the origin of force and extension, from the origin the graph extends to a point P. At that point, we say that the wire can still return to its original length, whereby the Hooke's law is fully obeyed. Now, if you look at what the word says, you said that metal wire stretch beyond its limit of proportionality. We're going to look at the stages where this can occur. But then let's look at it here. Now look at this. He said, this is area under the graph, that is strain energy per unit volume. We'll talk about this later in elasticity 2. Now, from the origin all the way to this point, we say that it is between the limit according to what Hooke's law stated. Then, a point Y, the material suddenly starts to stretch without any extra load. The yield point or stress is the stress at which a large amount of plastic deformation takes place, which constant with constant or reduced load. Now, at this point, then the material has really gone to become just a plastic. And then it will not be able to return to its original shape. So even when you remove the force, the body can no longer come back to its original shape. Then look at this point. He said at point E, look at this point E. What happens? The material starts to behave plastically. After point E, the material would no longer return to the original size and shape after the stress is removed. So now all these different positions on this graph is telling you what happens beyond that particular point. So at this point, normally what we experience here is breaking. The material breaks because the load is too much. You keep on adding, and then the load will not be able to carry the spring will no longer be able to carry the load again. We talk about that one as the 8 point. We also represented here. He said because, look at this, he said metal wire stretched beyond its limit of proportionality. He said when the load is removed, extension decreases, you know, then it comes back to original shape. That is what he means by extension decreases. Then the unloading line is parallel to the loading line. As the stiffness constant in the same, the force behaves between the atom are the same as during loading. So it returns back as if when you are loading, it extends. When you are removing it, it's gone back to the original shape. Then, now look at the next one. It said, because it is stretched beyond the elastic limit, it is deformed plastically, permanently stretched, so that unloading the line doesn't go through the origin. So what we are all saying between this one and the other part of the slide, we are talking about what happens when the material goes from obeying Ohm's law to not obeying Ohm's law. When we'll be using Examguide app, we are going to be looking at so many other UTME or JAMB questions that are related to this. Okay, let's tackle the question on the screen, and we are going to take it one after the other. If you look at the question, you notice that the natural length is 20 centimeter. So I'm going to call L sub naught, which is 20 centimeter. And then, the weight of a scale pan hanging freely on its lower end. When an object of mass, 40 grams, so I'm going to say M1 is going to be 40 grams. So in the pan, its length becomes L2 is going to be 21.80 cm. When the object is replaced with another mass, M2, 60 grams, the length becomes 22 L3, 22.05 centimeter. Calculate the mass of the scale pan. So the mass of the scale pan, I'm going to call it MS, which is unknown. So looking at this question, I'm going to have two stages, and I will apply the Hooke's law, general formula for the Hooke's law. But it gets a little complicated because of this mass of the scale pan. So the total force is going to be mass of the scale pan plus the weight of the body is going to be equal to KE. This is the formula I'm going to use. Because the total force here is going to be mass of the scale pan plus the weight of the object hung. So I'm replacing this F with this. Now, the mass of the scale pan, I have to convert this mass, 40 grams, to weight. And that is going to be mass of the scale pan plus 0.4, which is equal to K multiplied by E. What is the E? This 21.80 minus 20 is going to be 1.8 in centimeter. If I divide it by 100, I convert it to meter. So it's going to be If I divide this now, it's going to be 0.018 meters. So I'll have 0.018. Now, how did I get 0.4? Remember that weight is going to be mass times acceleration due to gravity. And then if the mass is 40, I will divide by 1,000, multiply by 10. 10 is acceleration due to gravity. And that is already what it is given here. So I'll multiply, cancel this and cancel this also. We have 10 divided by 4, which is going to be 0.4. And that is how I achieve this. So this is the first one. Then another one plus 60 grams is going to be 0.6 equal to K multiplied by 2205 minus 20 is going to be 2.05. If I divide it by 100, I'm going to have 0.0205. And then I will multiply it here. Now, I have to simplify this simultaneous equation because this is the first one and this is the second equation. To simplify this, I'm going to say equation 2 minus equation 1. And that is going to be, this minus this is 0. This minus this is going to be 0.2, which is equal to, and this minus this. So I will have 0.0205 minus 0.018, which is 0.0025. 0.0025 K. So K is going to be 0.2 divided by 0.0025. K is going to be 80 Newton per meter. So that is the constant. That is the spring constant or the stiffness of the spring or the force constant as the case may be. So the next thing we have to find is the mass of the scale pan. So the mass of the scale pan is going to be plus 0.4 is equal to 0.018 times 80. So mass of the scale pan is going to be 80 times 0.018. So I have 1.44 minus 0.4. So the mass of the scale pan is going to be 1.04 grams. That is in kilogram. It can also be given in Newton. So that is the answer concerning the mass of the scale pan. Now let's look at the second question. Now, a load of 50 Newton attached to free end of a spiral spring stretches it from 0.3 meter to 0.36 meter. Calculate the length of the spring when a load of 70 Newton is suspended from the end. So, I'm going to use this formula F1 over E1 equal to F2 over E2, which is all equal to constant. So, because I am looking for the extension of the two. However, let me tell you how it started. This is F is equal to KE, F1 KE1. Now, there are two extensions here. The E1 is going to be L1 minus L sub 0, and E2 is going to be L2 minus L sub 0. Now, in this one, L1 is 0.36, and this is 0.36 minus 0.3, and E1 is going to be 0.36, 0.3. So 0.06 meters. That is E1. So E2 is going to be, I don't know E2, L2 minus S sub 0, which is 0.3. So these are what I'm going to use for this problem. Now, applying this to this first one, because there are two forces. The first force is 50 is equal to K times E1 is 0.06. So K is going to be 50 divided by 0.06, which is 833.3 Newton per meter. Now, we're also going to have F2 is going to be K E2. Now, I don't know L2, and that is what we are looking for. So this is 70 is equal to, instead of K, I'm going to put 833.3 times E2 is going to be L2 minus 0.3. So 70 is going to be equal to 833.3 L2 minus 833.3 multiplied by 0.3 is going to give me 250. So 70 plus 250 is going to be 833.3 L2, and this is 320, which is equal to 833.3 L2. So L2 is going to be 320 divided by 833.3. So L2 is going to be 0.38 meters. Thank you. We have come to the end of this lesson, but before we go, we are going to take a few more exercises from Examguide app. The first question we have here, which relates to the lesson we have, is the point at which the molecule of a loaded wire begins to slide across each other, resulting in a rapid increase in extension is called. So in this case, we are looking at, remember, at the beginning of this lesson, we talked about the fact that Hooke's law can be obeyed when we have a kind of graph load and extension. So when you have this kind of graph passing through the origin, we say that Hooke's law is obeyed. But then when it starts extending to this part, we now say that deformation has occurred. So in this question, it said that a point at which the molecule of a loaded wire begins to slide across each other, resulting in a rapid increase in the extension. That means the extension keeps increasing. At that point, it's no longer going to be elastic limit. It's going to be called yield point. So looking at this one also, we said the diagram above shows the stress and strain graph for a typical metal rod. What does X represent? X represents the yield point. No, X represents the breaking point. That is the point where the object or the material or the spring breaks. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell, and share the video to people that will benefit from it. Bye.